I want to remind you what a homogeneous system is. So, reminder, Ax equals 0 is called homogeneous. Yeah. So what it means that the column vector B of the free coefficients is all 0 entries. Okay, so all the equations in the system are of the form a1x1 plus a2x2 plus a3x3 dot 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 equals 0. Okay, all the equations are of this form. And here's an observation. You can call it a theorem, but it's giving it too much respect. A homogeneous system maybe you can tell me, what am I going to write?
It will always have one solution.
Exactly. It will always have a solution. It can't have no solutions. Why? Because if you take x to be 0, if you take all the variables to be 0, it would solve it, right? Do you agree? Always has a solution called the trivial solution. Namely, take all the x's to be 0. Okay? Does everybody agree? Can you already relate to this and understand this in this matrix form? Okay, where I don't spell out all the equations. Okay, but what this says is take x1, x2, x3, x4, take all the x's to be 0, and then plug it into the system, you would get each of the equations satisfied, because a1 times 0 plus a2 times 0 plus a3 times 0 and so on equals 0, obviously. Good? Everybody? Okay. Here's an example. It's going to be a surprising one. Ready? Everybody? 1, 2, 3, 4. 2, negative 1, 1, 0. 3, negative 2, 1, 2. Times x1, x2, x3, x4 equals, what am I going to write?
13, 8.
No.
0.
Right. I'm gonna take the homogeneous version of this system of equations. This is the example that we kind of studied at length a couple of videos ago, but it had a 13, 8, 3, 13 there, right? It wasn't homogeneous. Now it's homogeneous. Do you agree that if I put 0, 0, 0, 0 here, it's obviously satisfied? Okay, good. So here's a theorem. Let's call it a theorem or a claim or whatever. If a homogeneous system has a non-zero solution, then it has infinitely many solutions. Why is this true? Why is this true? So think of here's the proof. It's calling it a theorem is again a bit giving it a lot of honor, but here is the idea. So suppose we're looking at the system Ax equals 0. This is what a homogeneous system looks like, right? Suppose x0, let x0 be a solution. let x0, which is not 0, be a solution. Okay? Then any multiple of this vector would also be a solution. Why? Then alpha times x0 is also a solution. Why is that true? What does it mean for alpha times x0 to be a solution? That if I put here alpha times x0, it solves it, okay? Because what is a times alpha x0? Alpha x0 is just taking x0 and multiplying all its coordinates by alpha. That's how we multiply a matrix by a scalar, right? Maybe I'll write it here just for a reminder if you happen to forget. So alpha times x0, so x0 is some vector of the form, in general, x1, x2, ... n is just, whenever we multiply a matrix, and a column vector is a particular case of a matrix, by a scalar, it's just multiplying every entry by that scalar. So this is the vector alpha x1, alpha x2, alpha xn, right? That's what it means to multiply a vector by a scalar, right? Okay, and what is a times alpha x0? So if you recall the properties of matrix multiplication, scalars were allowed to move freely. So think of this as a general matrix B. A times alpha B is the same as alpha times AB is the same as alpha A times B. Remember that property? So this is the same as alpha times AX0. Do you agree? And AX0 is what? Is 0, because that's our assumption that x0 is a solution. If you plug in x0, it solves it. So this equals alpha times the 0 vector, which is the 0 vector. Do you agree? Okay, so here, this follows from this assumption that x0 is a solution. And what we found is that, look, a times this vector is also 0, so this vector is also a solution. Good? Everybody? Okay. So if a homogeneous system has a non-zero solution, then it has infinitely many of those. And for example, just take multiples of that solution. They would all be solutions. Okay? So what this means is that a homogeneous system cannot have the case that we had in the general case where you have a unique solution. It either has no solution. Sorry. It either has, let's write that. Oops, where's the next page? So let's call it a summary. For a general system, we can have either no solutions or unique solutions or infinitely many solutions. Those are our three possibilities, right? And I even left here on the board the theorem that classifies these three cases according to the rank of the matrix and the augmented matrix and so on, right? Those were the three possibilities, okay? For a homogeneous system, that's no longer the case. There's always the zero solution, right? There's always what we call the trivial solution. So there can't be no solution, okay? So either there's just the trivial solution, or if you have any solution other than the trivial, you already have infinitely many. Those are the only two possibilities. Either it just has the solution x equals 0, or it has infinitely many of them. Good? Clear? Okay, let's do an example maybe. So it's on the board, right? Yeah. Here's the example that we wrote down over here. Okay, let's try understanding what are the solutions of this thing. What I want to do is I'm going to write a solution. You're going to easily verify. And we're going to discuss how I found it in a minute. Okay, so do you agree? Do you agree? So for this example, 1, 1, negative 1, 0 is a solution. Obviously, 0, 0, 0, 0 is the trivial solution, but I claim that this is a solution as well. Why? Let's plug it in and see that it solves it. So if I write here 1, negative 1, 1, 1, negative 1, 0, I get 1 times 1 plus 2 minus 3. 1 plus 2, 3, minus 3, 0, plus 0. I get 0. Do you see that? Let's do it for the second row. 2 minus 1 plus 0. 0. Good. And 3 minus 2, 1, minus 1, 0, plus 0. Do you agree that this is a solution? Okay. So this is a particular solution, a specific solution. And in fact, the solution set, or the general solution, is just multiples of this thing. So it's x, x, minus x, 0. Anything of this form would be a solution, and those are all of them. I'm going to show you how we found them in a second. Okay? Good? Okay. Good. So my next question is, how do the solutions of a homogeneous system, how do they relate to solutions of a non-homogeneous system with the same coefficient matrix? Okay? So let's maybe ask this. Let's go back to that board so we can leave this example because we want to discuss it further. So what is the relation, if there is any, between solutions of any system, AX equals B, and its homogeneous counterpart, same A. Okay? And it turns out that there is a relation, and that's what I want to discuss. And in fact, you can even figure out solutions to one by knowing the others, and vice versa. Okay? So let's try to explore that. So back to our example. I'm jumping between boards because I'm kind of this example is evolving as we extend the theory. So back to this board. So the solution to this is this. Maybe let's write it down here. Solution x, x minus x, 0. And let's remind you of the solution of the original, our favorite system. Equals 13, 8, 13. The solution of this system, the solution set, was x, x minus 3, 5 minus x, and 1. Remember? So how do they relate? and kind of just observing, just looking at it, you can see that in fact, the solution here, a general solution here, if you add 0, -3, 5, 1, you get the solution for this one. Do you see that? Do you see that this is this plus 0, -3, plus 5, plus 1? Do you see that? Everybody? That's going to be the general phenomenon. So the solution set of the homogeneous version differs from the solution set of the non-homogeneous version for the same coefficient matrix. Okay, of course, if you take different systems, there's no relation. But if it's the same coefficient matrix, the difference is just a specific vector. And that specific vector happens to be, it's not just any specific vector, that specific vector happens to be a specific solution for the non-homogeneous one. Okay, so if you plug in, what was it, 0, -3, 5, 1 into here, it's going to satisfy it. Okay, so that's going to be a theorem. We'll write it down in a second. So let's just build towards it with some more theory. So here's another, there's a question mark here. Okay, so here's a theorem. So it has two parts. One, if AX equals B has infinitely many solutions, then so does AX equals 0. Again, same A. And part 2, if AX equals B has a unique solution, then so does AX equals 0. Okay. Now, why is this true? Why is this true? In fact, this is really easy to prove. We're gonna see it in an example in a second, but it's really easy to prove if you think of the theorem about the ranks of A and A star. Okay? So let's do it, let's think about it carefully. I don't want to write all the details, let's think it out loud. So suppose we have a system, AX equals B, with infinitely many solutions. Let's look at the theorem that we had. It's still here on the board. When are there infinitely many solutions? Here. When the rank of A equals the rank of A star is less than n. Okay? So this was true since we are assuming that we have a system with infinitely many solutions. We know that this is the case. Do you agree? Now let's think of the corresponding AX equals 0 system. It's going to have the augmented matrix is going to have the same A here, but this is going to be 0 all along. And in all the row operations that we do in order to reach the echelon form, they're all row operations. Replacing this B with the zeros won't affect anything in any other column. Do you see that? Columns don't affect one another when we do row operations. Do you agree? Everybody? This is a key to understanding what I'm going to say now. When we do row operations, look at me. I'm an augmented matrix right now. When we do row operations, they're just playing games between the rows. A column doesn't affect another column. We can never change things in column 5 by doing something in column 13. Do you see that? We're replacing two things, we're adding a multiple of one to the other, we're subtracting, we're multiplying by a constant other than 0, but it's always between rows. So if we take this last column here on the right, if you take the last column on the right and replace it with zeros, all the row operations you do in order to reach the echelon form are going to be the same, and they're not going to do anything on this column because it had all zeros, and so it's going to stay all zeros. You're adding 0 times 0 this, and do you agree? Everybody? Okay, so when we reach the echelon form for a bar 0, this is going to remain intact. It's going to remain the same result. The rank of A is not going to change because we did exactly the same things to A, right? And the rank of A star is determined by the rank of A in this case. When can the rank of A star be different? If there was a non-zero row in A star. Remember that? If somewhere where the non-zero rows of A ended, but in A star there's still a little non-zero element, right? That's when this could happen, but it can't happen because A star in this case only contributes zeros. All of this is 0. Do you agree? So if these were equal and they were some value less than n, they're going to be equal for the homogeneous system as well, and they're going to have exactly the same value. So this is going to hold for AX equals 0 as well. Okay? It would take me something like maybe 15 minutes to spell what I just said out precisely, and I prefer not to do it. So I hope you understood what I said, and you can either rewind and hear it again, or ask questions, or think about it some more. Let's do the same argument for the second part of the theorem. Okay? So the second part said, if it has a unique solution, so does AX equal 0. Right? That was the second part of this theorem. Let's see that it follows just the same from that original theorem. So when does the original system, the non-homogeneous, have a unique solution? If the rank of A and A star equals and equals n. This cannot be overturned by changing B to 0. Okay? The only way to reach this is B having non-zero elements, ruining the rank, the quality of the ranks by allowing more non-zero rows in A star. Okay? So this would remain the same as well. Clear?
What if we have in matrix A a row of zeros? Wouldn't it change the rank of the augmented A in the matrix A? I mean, we have
the situation. Here's the picture. In where am I gonna draw it? The situation is this: you reached the echelon form. Okay, just in terms of just intuitively. Okay. Do you agree that the echelon form looks something like this? Where here you have ones, and all the rest is 0. Everything, all the leading coefficients are 1s, and over here in the echelon form, all of these are zeros. Okay? So here you have zeros, 0, 0, 0, and here you have zeros, I don't know how many, and here you have zeros, and so on. This is the echelon form. The rank of A is determined by counting how many non-zero rows you have. The rank of A star, in general, there could be a non-zero element here, which would make this the situation. But that cannot happen when this is all zeros.
Yeah, but that's what I mean. What if we don't have a homogeneous matrix, and one of the solutions on the last row is 1?
Here.
Yeah. So you have...
But that doesn't... This is a situation which is not covered in the theorem we're tackling. The theorem asks, if there's a unique solution here, meaning this is the case, then there's a unique solution in the homogeneous one. If there's infinitely many solutions, then there are infinitely many solutions in the homogeneous one. It doesn't say anything if there's no solution to the non-homogeneous one, and the reason is because we already know what happens then. The homogeneous is still going to have solutions because it always has solutions, because it has the trivial solution, right? So the corresponding statement to this, a statement of the form, if AX equals B has no solutions, then AX equals 0 has no solutions, is false. Because AX equals 0 always has solutions, at least one, the trivial one. Clear? Okay, so I hope this helped to some extent. We're playing a tight game of time here, okay? I wish I could do this the real way and prove everything, but that has a price, okay? And we don't have that time. Okay, so let's go back to our example here. Let's go back to this example and kind of try to solve it for both of these situations in order to see why that theorem is valid. Okay, I think maybe in an example it would be clearer. So we already know how to solve this one, right? We took the coefficient matrix, the augmented matrix, 1, 2, 3, 4, 13, 2, negative 1, 1, 0, 8, and 3, negative 2, 1, 2, 13. And then we did a whole bunch of row operations, which I'm not going to, of course, do again. Oh, let's do it again. It was fun, right? Nah. So we know what we got to at the end. Let's write the final step, the reduced row echelon form, the canonical form. Okay. So what we got to was this: 1, 0, 1, 0, 5, 0, 1, 1, 0, 2, and 0, 0, 0, 1, 1. Okay, so here there is many steps, many row reduction steps. Okay, good? And this yielded the solution, which was this, right? We solved the system of equations corresponding to this. It was a very simple form, and these were the solutions, right? Now let's solve this one. Okay, let's go. And this we haven't solved yet. We have to do all the steps from scratch. 1, 2, 3, 4, 0, 2, negative 1, 1, 0, 0, 3, negative 2, 1, 2, 0. That's the augmented matrix corresponding to the homogeneous system. Do you agree? Okay, and I'm going to do the following steps. I'm going to do exactly the same steps that I did before. Exactly the same steps. Okay? There were 15 of them. I don't remember exactly. I'm going to do precisely the same steps. Do you agree that what I'm going to get is 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, and 0, 0, 0, 1, 0? That's what I'm going to get. Do you agree? Because these were all row operations. Whatever they did to the rows, they're going to do the same thing, except here they did something mysterious. We don't know, well, we do know, but it's hidden in this many steps statement. They got this to this, but if this were all zeros, it's just going to be all zeros at the end as well. Do you agree? Okay, and now what is the solution to this? Well, I know how to solve this. This corresponds to x1 plus x3 equals 0. x2 plus x3 equals 0, and x4 equals 0. That's the system. And this means that x4 is 0. Take x1 as your independent variable. x3 is minus x1. And x2 is x1. Do you agree? Good, everybody? Okay, so in particular here we had infinitely many solutions with 1 degree of freedom, and same for the homogeneous one. Do you agree? Okay. By the way, maybe a remark. So everybody good with this example? Questions? Okay. So by the way, maybe we should say a remark here that the converse to that theorem is false. It's not that if the homogeneous one has a solution, then so does the non-homogeneous one. Okay, and here's an example. So remark, the converse, the other direction of the converse to the previous theorem is not true. So when you want to say that something is not true, How do you argue that a fact is not true?
Example.
Right, you just need one counterexample. One. Okay, so here's a counterexample. So what do I want? I want a system that where the homogeneous one has, for example, infinitely many solutions, but the non-homogeneous doesn't. Okay, so here it is. Take the system x minus y equals 3 and x minus y equals 4. This is a non-homogeneous system. How many solutions does it have?
0.
No solutions, right? So this is non-homogeneous. And no solutions. These two equations contradict. Do you agree? But the corresponding homogeneous one would be x minus y equals 0 and x minus y equals 0. That's the corresponding homogeneous one. And it has a solution. In fact, it has infinitely many of those. Okay, so this is the corresponding homogeneous version. Infinitely many solutions. Right? Any x equals y would solve this. Take x and y to have the same value and they would be a solution. Do you agree? Okay? So it's not true that if this one has infinitely many solutions, then so does the non-homogeneous. That's false. That's the other direction of that theorem. Okay? Okay. Good. So the last thing we wanna discuss is the fact that we kind of observed in this previous example. It was here on this board. The relation between these two. Okay, how do solutions to the non-homogeneous relate to solutions of the homogeneous? And we saw that it's obtained by just adding a fixed vector. Okay, so here's the theorem. Here's the theorem.
About the counterexample,
Mm-hmm.
it doesn't work with any sort of solution we find, right? So we find that the homogeneous has a unique solution. It doesn't say anything about the non-homogeneous, right? It's the same thing.
Well, there is a relation. I'm going to write it right now. So we're gradually exploring what does hold and what doesn't hold. Okay? The other way to the theorem we had here is false. That's the counterexample. The counterexample exhibited a situation where the homogeneous had infinitely many, but that doesn't apply, that so does the non-homogeneous. Okay? The theorem said that if the non-homogeneous has infinitely many, so does the homogeneous.
So now we're referring to the case where the homogeneous has a unique solution. What does it say about the non-homogeneous?
No. Let me write it. Let me write it. Okay? So the theorem that I'm going to write now, it's going to start with an if. Okay? And it's going to assume that there's some solution. If x0 is some solution, is a specific, a particular solution of the non-homogeneous system, of a system of equations, any system of equations, then the solution set, the solution set of ax equals b, which may be just x0, or maybe infinitely many of them, because we're assuming there is one solution, equals this specific x0 dude plus the solution set, the general solution of ax equals 0. This is an equality of sets. This is a bunch of solutions, all the possible solutions of ax equal b. And this is a bunch of solutions as well. It's all the possible solutions of ax equals 0, where you take them and add x0. Okay? So in the example, in the previous example that we kept referring to throughout this clip, in the example, we had x minus 3, 5 minus x, and 1. I'm writing it in column vector form, just to make it easier to express. This was equal to 0, negative 3, 5, 1. This is the x0. This is the specific solution to the non-homogeneous one, plus the general solution of ax equals 0, which was x minus x 0. Good? Okay. Now, why is this statement true? Why is it true? I'm debating with myself if I want to spell out the proof. It's not a hard proof. It's in fact straightforward. You just have to let me say it, and according to the time we have, we'll decide if to spell it out. So what do we have to prove? We have to prove two things. We have to prove that if we take a solution of ax equal b, we can write it as x0 plus some solution of ax equals 0. And the other thing we have to prove is that if we take a solution of ax equals 0 and add x0 to it, we get a solution of ax equals b. Right? Those are two different things to prove. Take an arbitrary solution here, show that you can write it as x0 plus something here. Take an arbitrary dude here, show that if you add x0, you get a solution here. Okay? So those are the two things that you need to prove. So maybe let's write that. I think that's what we'll do. We'll write what you need to prove, and you guys are going to try to prove it. It's kind of straightforward. There's no need to go into too much detail. So proof, show. 1, take y0, a solution of the homogeneous one, and show that x0 plus y0 is a solution of the non-homogeneous one. Good? Let's do it. It's a one-liner. Let's do it. What do I need to show? I need to show that this is a solution of this. Here goes. What does it mean to show that it's a solution? I need to show that if I plug it in, I get B. Right? If I plug this into this system, I get B. That's what it means for it to be a solution, right? By distributivity of matrix multiplication and matrix addition, this equals ax0 plus ay0. These are properties of matrices that we already know. What is ax0?
0.
No. B. Because x0 was a specific solution of the non-homogeneous system. Look at the theorem on that board. Okay? If x0 is a specific solution of ax equals b, that means that ax0 is just b. And y0, we're taking y0 a solution of ax equals 0. So ay0 is 0. That's it. The second thing we need to show, if, let's call it x1, is any solution of ax equals b, then there is a solution, let's call it y1 of ax equals 0, such that the solution of the non-homogeneous can be expressed as the specific x0 in this theorem plus this solution of the homogeneous. That's the second thing that we need to show. Okay? If you're a bit confused now, because we've been going for quite some time now, and you may need a rest, then press pause, go have some coffee, come back. Well, you guys are sitting here, you can't do that, huh? But you guys at home, press pause, go have some coffee, come back, read this, it will be clear. It's not a sophisticated statement. It's just a matter of understanding what you need to show and why it holds, okay? And indeed, I'm going to tell you what the y1 is. Take y1 to be x1 minus x0. x1 is a solution to the non-homogeneous, so is x0. And let's show that this is indeed, that y1 is indeed a solution of ax equals 0. So, of course, if we do this, then x1 is x0 plus y1, so this is obviously satisfied, right? If y1 is this, then this is trivially satisfied. What we need to show is that y1 is indeed a solution of ax equals 0. Okay? So a y1, we need to show that this is 0. A y1 is a x1 minus x0. That's how we defined y1. Again, by distributivity, this is ax1 minus ax0. And both of them are b. And that's it. Okay, it's really not too sophisticated. It just may be confusing because of sometimes simple statements are confusing because wait, what do we need to show? Why did that show that? And so you may need to think about this a bit more. Okay, I wanna just write one final remark and then we'll stop. We need to finish here. So one last remark. Let's call it a corollary. What does it have a double? Double L, double R, double Y. It has something double. Corollary is something that follows from a theorem. Okay? So the corollary is, if we know the solution to ax equals b, yuck. The solution to ax equals b, then we can find the solution to ax equals 0 easily. How? Suppose we knew the solution to ax equals b. We had it, so example, we had the solution x minus 3, 5 minus x, and 1. That was the general solution to ax equals b in the example. Take any particular solution you want. Subtract it. Take the general solution, subtract a particular solution, you're going to get the solution set of ax equals 0. Okay, it's straightforward from this theorem. So let's take any solution you want. Let's say x equals 2. So we get 2 minus 1, 3, 1, and subtract it. What do we get? We get x minus 2, x minus 3 plus 1, x minus 2, 5 minus x minus 3. So it's 2 minus x, and 1 minus 1, 0. This is the solution to the homogeneous one. You're going to say, whoa. The solution to the homogeneous one in this example was x minus x0, right? This is the same thing. X minus x0 is the same set of solutions as x minus 2, x minus 2, minus x minus 2, 0. Do you agree? Everybody? Okay, so just by subtracting x0, you can get a general solution to the homogeneous one if you know a solution to the non-homogeneous. Okay, so solving the non-homogeneous is always sufficient. Okay, so this wraps up this one. Sorry for taking a couple minutes more, and we'll continue next time. האמת שמה שאני רציתי לבקש